Good afternoon, everybody. Today, I'm going to present our research work titled Integrating Advanced Distance Metrics with Route Navigation Systems for Biosecurity in Livestock Transportation. So, a bit of context about what I'm going to present to you. So, we will start with an introduction and a background about the problem we aim to tackle. Then I will go on with the proposed solution that aims to fill the gap about the problem I'm going to present you. Sorry for the overlap of the text. I will present material and methods we employed to implement our solution. I will delve in how we manage the risk, both in the sense of risk related to buffer zones and risk assessed after the route calculation. I will provide a use case example, and then I will derive a few conclusions. So the main problem is that, as you know, infectious disease poses significant threats to animal health and public health and agricultural economy. But models usually rely on Euclidean distances that usually fails to capture real-world complexities. And this fits the need for advanced tools that integrate this kind of data to provide a more comprehensive understanding and analysis of disease transmission. So, although natural elements such as mountains or friction elements, lakes, water bodies, etc., can act as a barrier, previous researchers highlighted how anthropogenic variables like human population density, roads, etc., can be a proxy for indirected contacts due to human-mediated activities, and also in particular the movement of livestock and animal-related products. So the main point, as you will have understood up to now, is that existing navigation systems lack biosecurity considerations. In other words, there is no integration of epidemiological data in routing systems. So we propose with this research a route navigation tool that incorporates biosecurity risk levels in order to allow stakeholders to make informed decisions about livestock transportation. So shortly, in our system, we employed as a data infected farm locations. We computed around this location radius, and to effectively compute paths, user at each computation should provide start and end coordinates. The buffers then are determined around these points automatically with a parameterized radius that is constant for each farm. And then the risks for what is our research activity are just assigned from veterinary epidemiologists, and for our use case, we just determine them synthetically using a uniform probability distribution. Then, for what concerns the methods, our system is capable of providing 3 different types of distances, namely low-risk routes, balanced routes that balances the risk exposure and the distance, and finally also shortest routes, normal shorter routes that does not take into consideration any risk determination, just to compare it with low-risk distances, low-risk paths. So this is our application architecture. Basically, this is a web application that employs normal front-end technologies, but is backed by a routing engine, namely Grasshopper, and a PostGIS database that collects and allows to fetch farms locations data. We use OpenStreetMaps to just have a map on the background. So here comes the tricky part. So basically, the key concept is that risk, as I told you, are assigned synthetically in our scenario, but are intended to be from the lowest to the highest proportionally. So namely, risk 1 means full risk, while risk 0 means no risk. But for the technology we are employing, namely Grasshopper custom models, this is undouble in the sense that he reasons with the complementary. So 1 is no risk and 0 is getting close to 0 is high risk. So we took the complementary risk assigned to each farm, and we classified them as in groups that goes from 1 to 10, as GraphOper accepts groups of geometries that have a risk that are it is discretized and not continuous, so we must group them. And the important part is that we weight these risks in order to emphasize high risk areas, and instead we let me resume. We weight these buffered areas in such a way that high risk areas that are classified in lower classes are even more weighted to be under risk. And instead, for what concerns shortest area, we just assign a risk that is 1. So for the custom GraphOper custom models, there is absolutely no risk, so that value is ignored. After that, after the engine retrieves a path, this path is intersected with the actual buffers, because the routing engine uses heuristics information about the risk of the buffers. And the risk is then assessed again to understand whether it actually the computed path is actually a risk or it is not. Basically, the risk is retrieved, and it is classified to be no risk if the path does not really cross any risk area. It is low if the overall average risk is under 2, is medium if it is between 2 and 5, and it is considered to be high otherwise. So this is our interface, and we can see in this simple example that with this implementation, the retrieved path from the routing engine effectively tries to avoid infected areas. Circles in here represent buffers, and the colors represent the risk. As it gets closer to red, it is more risky. And the use case that we are presenting, that is this one representing this visual representation, allows you to understand how the actual web application works. So the user can configure the environment by uploading a shapefile containing points related to farms. This is not a mandatory operation, in the sense that if no shapefile is provided, simply it uses the data stored in the PostgreSQL database. Otherwise, information about farms are updated. The user inputs the coordinates, the start and end coordinates. To be completely fair, now we updated the application in such a way that it accepts also textual addresses, and it uses a service to translate these addresses in coordinates in APSG 4326. The query is submitted to the routing engine that, alongside the custom models provided, tried to determine the low-level balanced and shorted routes. The path is retrieved, as well as in the meanwhile, the average risk score is assessed by intersecting the retrieved path with the buffers, and the level is assessed. Note that the three risk levels have been defined in our research by inspection, and we basically tried and determined whether, in opinion of a veterinary epidemiologist, it was actually a low-risk route, a medium-risk route, or a high-risk route. And also path information is returned, such as the total distances and distance and the directions. User can toggle between these risk levels. And for this simple use case, we can see how, I can point maybe the laser, we can see how while the shortest path, which is, as I told you, actually the shortest path without any consideration about the buffer risks, has a lower length, like 53 kilometers. It has an average cumulative risk index that is of 15.8, and it is classified, as I showed before, as high risk. while balanced and low risk route are way longer, like 2 or 3 times, but they can effectively reduce the risk, the overall risk in the path. So we effectively set up a routing system integrating epidemiological data, and we observed how, while accepting a trade-off in terms of the total distance, we can effectively reduce the risk associated with the transportation, the livestock transportation. At the moment, we consider the risk associated with each buffer to be constant, but in future, we plan to consider also the distance from the buffer center in the risk assessment phase. That means how close you pass through the buffer center. And future considerations will also be taken into consideration about how to fine-tune the weights for each route and how this may impact the trade-off, for instance, distance risk. And we also expect to run multiple experiments on the path computation and to get interesting results. So thank you.